Hey guys, so we did the conversion and we also did the incremental step theorem. So now we're going to put that into a material balance and come up with a generic equation that we can use on any reaction ordered plug flow reactor. So it's not, I'm not going to say very simple, but once you have this equation, the problems with this type of reactor become simpler with practice. Okay, so there's your differential plug, D of V. I like to draw it off to the side because it makes me keep in mind that I'm dealing with a differentially small element, especially when I'm doing the balance. Okay, so generic equation is in minus out plus your generation term is equal to accumulation. Now, for anything that has a continuous flow going through it, at least for this class, it's usually going to be at steady state. Pretty sure there's a chapter in the back that does unsteady state, and then the equations get a little more advanced. You have to use MATLAB. There's a lot of stuff there. But for now, accumulation is equal 0. So now your in becomes your molar flow rate in, which is FA naught. I'll draw it over here. FA naught. Your out from the differential element is FA minus FA plus a generation term, which is RA times D of E. And the volume is D of E, right? D of E for the small element that you're dealing with equals 0. Okay, so for the incremental step theorem, I'm going to write this stuff off to the side here so we don't lose track that we're trying to get to the solution for this balance. Okay, so first off, FA, what is that equal to? It's going to be equal to two things, right? FaO1 minus X. That's the first one, using conversion. The reason why that is because you do 1 minus x, because conversion is the amount of A that leaves. So if it's, let's say in the last example, I believe it was 10 and 6 we used, but let's say 40% was converted. So what this equation is going to give us is 60% is not converted and is hence left over. So you use 1 minus x, it'll give you what you're looking for. It'll give you the amount of A that's left. Okay, second thing, for the incremental step theorem, you can also rewrite this and say FAO plus DFA dV dV, like that. And this is basically, like we discussed in the last video, is y equals mx plus b, where this is your m, this is your b, this is your y, and that's your x. So really y equals b plus mx, same thing. And it gives, basically, you have this going into the plug flow, and this is what changes. And you're assuming that the molar flow rate of A, or the presence of A, is changing linearly. And DFA, dV will be negative, because you're going to have a negative change in A. At point 2, you have a smaller change in A than point 1, and when you subtract them, you get a negative value. So DFA over dV will be a negative value. So I'm going to plug this guy into the balance, and you'll see how it works, hopefully. Okay, so you got FAO minus, I'm plugging in the one with the star next to it. What was it? Sorry. Minus FAO minus D of FA over dV times dV. And then don't forget to put in your generation term. So again, in green, I'm plugging in this guy. Okay, now here's the reason why we used it. I'll do this one in a really cool color. FAO and FAO will subtract from each other. But now you're left with dV, dV. That's why we use that equation, because we can get rid of the dVs. Now, what are we left with? Right here. This is exactly what we're left with. Equals negative RA, just like that. So I can cancel out these signs. Okay, so we're almost there. Now, we used the incremental step theorem, so I wouldn't have discussed the conversion or definition of conversion, at least for FA, if we weren't going to use it. So let's write FA in terms of conversion, right? So it's going to be FAO times 1 minus x. This gives you FA. And basically, I don't have FA over here. I have DFA. So basically what we got here is DFA over dx. That's what I want to get at. Well, what's the derivative in terms of x over here? Well, if we distributed the FAO, we'd have this equation. And then if you take it simply in terms of x, you're left with just negative FAO. Like that. So then DFA alone, without the dx under it, is equal to negative FAO dx. Now that's something we can plug into what we got over here. Right? So replacing DFA, we get negative FAO dx over dV is equal to positive RA. trying to keep the signs consistent. Now I'm going to move the negative over to meet with the RA, because usually when we're given the reaction rate, it's in terms of the disappearance of A, which makes negative RA. So, okay, here we go. dx dV is equal to RA negative. Now, let's move this stuff around. I want volume on one side and conversion and everything else on the other side, so we can size reactors. So then what you end up getting is dV is equal to, flipping it upside down, dx and dx will move over to this side like this. Negative RA will be in the denominator. And then, if you flipped it, FAO will come over here. Now you could double check with that by taking steps and being cautious, but that's what you end up with. So this is the generic equation. I should put here, 0 to V, this would be 0 to X. So your generic equation is basically the volume is equal to FAO, 0 to X, like this, dx, negative RA. And you'll use this one for all your stuff. Negative RA can be substituted in for first order. In case it looked like this. Negative RA could be substituted in terms of second order, and so forth. Now, I got a little bit of time, so I might want to go into doing an example. I'll do it with the first order. And the derivatives are pretty easy. They're not that hard. Or, sorry, integrals. So let's take FAO, right? Just taking the generic equation, 0x dx with KCA. Right? It's positive because negative RA is equal to KCA. Now, for CA, here's the trick. So like we did with the FAO, I'll do the FA like we did here. We said it was like this. So with concentration, you can say it's like this. Very similar. Here's the proof for it. FA is going to be equal to CA times Q for volumetric flow rate, and CA is equal to, So if this is the case, let's plug that into the equation above. CAQ, I mean by this equation, CAO times Q 1 minus X. And you divide the volumetric flow rates out, hey, look what we got. Like this. So we're okay. This works too. So basically this equation works as well. So we can use that. V is equal to FAO X dx over K CAO 1 minus X. This equation, this little bit you'll get used to doing a lot. Let me erase that. It looks like a division sign. Okay, let's finish up the integral. CAO times Q, that's replacement for this guy. K CAO, pulling them out of the integral because they're constant, is equal to this. Okay, now that's from 0 to X. Now V is equal to Q over K, 0 to X, dx over 1 minus X. Now I'm going to have to hurry up here, do this integral. We're running out of time. Okay, negative dx, right? So V is equal to Q over K, right? I'm going to place that with U, and I'm going to flip the bounds. So basically, it should be going like this, like that, du over U. But I'm going to use that negative sign, I'm going to flip the bounds. Like this. Right? Du, U. So then volume is going to be equal to Q over K times the natural log of 1 over 1 minus X. And then you're done. So if you got conversion, you got the rate constant, you got the volumetric flow rate, you can size the reactor. Again, let me write that one more time without all the circles. Okay, hope you liked the video.